So in special relativity, which involves not just rotations, but boosts, Lorentz boosts, we can take tensor products of 4 vectors. So if we have 4 vectors, v mu, w mu, and x mu, okay, so imagine some 4 vectors, we can construct a tensor product object v mu, w mu, w nu, x rho, and you see that mu takes 4 values, nu takes 4 values, and rho takes 4 values. So this object that we've constructed has 4 into 4 into 4 components. Okay, so that's 64 components, and this is called a rank 3 tensor. A mu nu rho. And we don't have to start with 4 vectors. We could imagine that there are just objects A mu nu rho, which are intrinsically what we call rank 3 tensors. And we say that the dictionary for transformation of these rank 3 tensors would be something like this. So if I want to know what this is in a primed frame, so A mu nu rho, this would be related by our transformation matrix lambda. So lambda mu alpha, lambda nu beta, lambda rho gamma, A alpha beta gamma. So the components A alpha beta gamma are the components of A in the old reference frame S, and there's an implicit summation again over alpha raised in lowered indices, beta raised in lowered indices, and gamma raised in lowered indices. Okay, and this is the transformation law, which is again simple in index notation. And so the most general rank n tensor that I can write down is something like this. So A prime mu1 to mu n. This is a rank n tensor. And this transforms in the following way: lambda mu1 nu 1, lambda mu2 nu 2, lambda mu n nu n, A nu 1 to nu n. Okay. So this is the same rank n tensor in frame S. This is the same rank n tensor in frame S prime, where the frames S and S prime are related either through a Lorentz boost or a rotation. That is, they're related by any element of the Lorentz group, any matrix lambda of the Lorentz group. So in the special case where the object A has no indices, okay, so an object with no indices, this object will be the same in the frame S prime. Okay, so such an object is called a Lorentz scalar. Okay, so things like the space-time interval that we've seen, for example, are Lorentz scalars. Okay, or the speed of light is a Lorentz scalar. It doesn't transform from one reference frame to another. Whereas things that transform, we have now derived the most general dictionary of how things can transform. Things can transform either as rank 0 tensors, which is to say they don't transform. They can transform as rank 1 tensors, which is to say that they transform as contravariant 4 vectors. They can transform as rank 2 tensors, rank 3 tensors, and so on. Okay, you can go on constructing higher and higher rank tensors, and you can get dictionaries for the transformations of these tensors. The challenge is to know what objects transform like which rank tensor. Okay, that statement is the non-obvious statement. How different things, which rank tensor do these objects transform as? So we had to derive, starting with the fact that the speed of light is constant for all observers, we figured out that this quantity transforms like a 4-vector. Okay, which we called the position 4-vector x. And all the other transformation laws were derived from the transformation law of this 4-vector. Okay, so all our other transformation laws were derived transformation laws. But in some cases, you might just have to guess what the correct transformation law is, and nature will tell you whether this is the right transformation law for the collection of objects that you're trying to describe. Okay, so it's not always possible to derive transformation laws. Sometimes you have to guess what the correct transformation law is. But among the possible guesses, everything should be expressible in terms of tensors of some rank. Okay, either rank 0 scalars, rank 1 4-vectors, rank 2 tensors, and so on. So this here is the most general dictionary of Lorentz transformation. Okay. So we will see specific examples of different objects that transform in these more complicated ways later on. And finally, I'll just show you one more thing, which is supposing I have a rank n tensor of this form. It's possible to define, so here all the indices are upper indices. Okay, so these are called contravariant indices. And it's possible to define a similar object where some of the indices are lowered. So for example, if I lower the kth index, but keep the other indices raised, this can be related to the original A by something like this. So G mu k nu k A mu 1, and wherever I was supposed to have the mu k index, I put in a nu k index. So this lowers an upper nu k index to a lower mu k index. Okay, so this is in the frame S. This is also an object in the frame S. Okay, this is not a transformation of reference frame. This is just defining an object which is made up of the old collection of objects that we had. Okay, just as for a 4-vector, a contravariant 4-vector, we can rearrange the components slightly to get the covariant 4-vector. And the lowered indices transform with this matrix. This is the transformation for lowered indices that we've seen for contravariant indices. And lambda is the transformation rule for upper indices. Okay. So sometimes you get what are called mixed tensors with a mix of covariant and contravariant indices. Okay, this will be useful when we start taking dot products. So for example, we could take a dot product of a tensor. So again, suppose we want to take a dot product of the kth entry of this with a vector v alpha. So what we would do is we would multiply by g, and we would sum over mu k and alpha. Okay, so it's useful to so this is some kind of special dot product where we're taking a dot product of v with the kth entry of this tensor. Okay, so this is like if we have a moment of inertia tensor in rotations, and we take a dot product with, let's say, the angular velocity omega about the I-axis, and a dot product with omega about the J-axis. This would be related to the energy, okay, of a rotating object. Okay, so that's why you might want to consider these kind of dot products. And so this kind of dot product can now be easily written by using mixed tensors. So with mixed tensors, you would write a mu1, and then in the location of the kth index, I lower the index and I write v with an upper index. Okay, so this is a partial dot product of this tensor with a contravariant 4 vector. So that's where these mixed tensors can be useful. Now, two more things that I'd like to tell you is one is when you have a tensor, let's say with all upper indices like this, it's also possible to take a dot product of two indices, let's say the ith entry and the kth entry. Okay, so you can take a dot product by simply multiplying by g mu I mu k, and then doing the summation over mu I and mu k, which is implicit here. Okay, so what this would do is if you have a rank n tensor, taking the dot product of two indices lowers the rank so that the new object that you get is a rank n minus 2 tensor. Okay, you can check that this new object would transform as a rank n minus 2 tensor. So it's only the number of what are called free indices, that is the indices that are not appearing in pairs of upper and lower indices, which are summed over, but rather the unpaired indices, which are free. You're free to choose the values of those. It's the number of such free indices that determines the rank of the tensor. Okay, and finally, it's possible if you have two tensors, let's say one of rank n, another tensor of rank m, it's possible to construct a tensor product of both of these, just as we constructed tensor products of 4 vectors. So we can consider the object or the set of objects. So it's a multiplication of just numbers. Okay, so for each value of mu1 through mu n, we take the corresponding component of the tensor A. For each value of nu1 through nu m, we take the corresponding component of the tensor B. And this gives us what is called a tensor product. Okay, and we multiply these two numbers together, and that collection of objects is a tensor product. And you can easily see that the rank of this tensor, this new tensor, is n plus m. Okay, so this gives us some new object that transforms differently under Lorentz transformations. It transforms as a rank n plus m tensor. Okay, you can similarly construct tensor products of tensors which are mixed, which have mixed covariant and contravariant indices, which I won't write down, but it's an easy generalization of this idea of tensor products.